Hey Pamela, it happened again.
What happened?
Well, SpaceX launched a bunch more Starlink satellites over the weekend, again, and China's Hyperbola 1 failed, again.
Yikes. And double yikes.
But we do have science on the origin of carbon and rocks.
That's better. I also found new 3D images of interstellar blobs and filaments.
And Beth will be interviewing the new PI for the Osiris Rex mission extension.
All that and more, right here on the Daily Space. I'm your host, Dr. Pamela Gay.
And I'm your host, Eric Mattis.
And we're here to put science in your brain.
There were Starlink launches this weekend, of course. 2 launches, each with 53 satellites. The first launched from Slick 4E at Vandenberg, the other Slick 40 at the Cape. One of those even used a brand new booster, which is unusual for Starlink. They usually fly on the boosters in the fleet with the most flights. 13 is the current record, and that was the Starlink. Both boosters and sets of fairings were successfully recovered on their respective ships and brought back for additional flights. The team liked the views from the first staged camera on the launch from the Cape, so here's a little long-cut landing video, which as usual includes a few cuts to the second stage camera before the first stage touches down. So sit tight, don't touch that dial, and watch a rocket come back from space. Also over the weekend, Chinese company iSpace launched their 4th Hyperbola 1 rocket. Like the last 3 launch attempts, this one also ended in failure. No official reason for the failure was disclosed. State media outlet Xinhua only said that, quote, the launch mission was abnormal. On board was another Jilin 1 series satellite to replace one launched in the last Hyperbola 1 launch failure. The Hyperbola 1 rocket has worked once, but that was a smaller, less capable version of the rocket. All 3 attempts to launch the larger vehicle have failed. From the latest roundup of rocket news, we take you to a story about carbon, a building block for life.
Carl Sagan famously said that we are all star stuff, meaning the atoms and molecules that make us up as people, as creatures, as being. We're all created in the violent explosions of stars. But understanding just how some of those elements came about has been a challenge to researchers. In a new paper published in Nature Communications, a team of scientists has uncovered just how one major life-building element, carbon-12, was produced in those stellar explosions. First off, there are 3 isotopes of carbon. We know of carbon-14 as a radioactive isotope used in dating organic material. The other 2 isotopes are carbon-12 and carbon-13, both of which are stable isotopes, meaning they don't decay. Of those 2, carbon-12 makes up over 90% of the naturally occurring carbon in our universe. And in the paper, the team explains how 4 alpha particles, helium-4 atoms that have 2 protons and 2 neutrons, can cluster and eventually stabilize and form carbon-12. They used first principles in their calculations, which is neat because it means they didn't add anything we didn't already know, and this can be assigned as a homework problem to graduate students. This is pure maths at its finest, and because it was rather complex maths, it took them over a decade to design the software and code and statistical learning techniques to crunch all the numbers. Questions still remain about when and where the carbon-12 gets produced. Co-author James Very is curious if these atoms come from the internal processes in stars or supernova explosions or even collisions between neutron stars. He notes, quote, "This nucleosynthesis in extreme environments produces a lot of stuff, including carbon," end quote. We look forward to seeing where this research goes in the coming years. Understanding the origin and timing of life and world-building materials is important in science. All of this work is tied together in the larger quest for understanding how life came about and can we find it elsewhere. A rock can tell you something new about the world and how it changed over time. Now, using mantle rocks found in the jungles of New Guinea, researchers may have timed just when the mantle under the region melted. These lowermost rocks are different from ones found elsewhere on Earth. They're full of elements that generally don't like to be in melted rock. They lack elements that do prefer to be in melted rock. So scientists thought that meant they were extremely old and formed during the Archean epoch, about 2.5 to 4 billion years ago, when the mantle was much hotter and therefore more liquid melt was available. However, that turned out not to be the case. Using radioactive dating, the team discovered that the mantle in this region melted during the Phanerozoic period. Unfortunately, it covers everything from about 540 million years ago until now. More dating is going to be needed to get a more precise timeline of events, and more research is needed to understand just how the mantle melted in this manner at that time. Science takes time, everyone. Coming up next, the shape of things in our universe. Stay tuned. Our ability to understand our universe is constantly frustrated by our inability to get a different perspective on the 3D structures that litter the sky. If you're lucky enough to live in the southern hemisphere, a peek into a telescope at the Tarantula Nebula reveals clouds of gas and dust and starlight that are arranged just right to trick the mind into seeing a spider's face. This is just a fancy game of shadows, however, and the actual structure of the clouds, if we could build them from clay, look nothing like the creepy crawlers that cause so many people to look away. This lack of being able to readily see in 3D means that when astronomers look at objects like the California Cloud and Orion A Cloud and see similar looking silhouettes, we don't know if they're actually similar. We also see in these two particular systems very different amounts of star formation. This dichotomy of similar looking clouds doing very different things has led folks to ask, why? Honestly, part of what makes scientists successful is that their internal dialogue sounds a lot like a 2-year-old who just keeps asking, but why? Unlike your standard 2-year-old, astronomers recognize they have to find answers for themselves, and with enough technology, they do. For this particular, but why don't they form stars the same question, researchers led by Sarah Rizet combined stellar locations from the Gaia mission with maps of gas and dust from the WISE and 2MASS catalogs to determine how much dust and gas is between us and stars at different distances. If two stars are side by side in the sky and both have the same amount of dust between us and them, we know all that material is closer to us than the closer star. If instead we see a small amount of dust between us and the nearer star, we know the bulk of the material is between that nearer star and the more distant one. Altogether, this team measured the amount of gas and dust along the line of sight to nearly 200,000 stars and used that information to come up with three-dimensional shape models of these nebula. The Orion A cloud was found to be denser with both filament-like structures and a prominent ridge of material. These dense regions drive star formation. At the same time, what appears as filaments in the California cloud were actually alignments of a sheet of material that is being shaped by a bubble pushing up. Where parts of the sheet overlap, we see filaments. At first glance, our view of the universe is very much Plato's shadows dancing on a wall. But with hard work, as is shown in a pair of papers in the astrophysical journal Letters and in Astronomy and Astrophysics, we can transform that shadow play into a 3D reality, which is admittedly a projection of a more than 11-dimensional reality, but that's a story for another day.
Instead of nice-shaped filaments, this next story highlights a galaxy that's really just a big blob. UGC 10143 lurks out in the center of a galaxy cluster, Abell 2147, which is located a hair under 500 million light-years away. This galaxy is the brightest one in that cluster. What's so exciting about this diffuse cloud of stars is the idea that elliptical galaxies may form when other galaxies merge. UGC 10143 was imaged because it was the brightest galaxy in its cluster, and like all such galaxies, were formed by the slow merger of infalling systems that were drawn in by its massive gravitational pull. Researchers used the Hubble to study the globular clusters that surround this galaxy and likely preserve the history of the mergers. This image uses data from the Hubble and the Pan-STARRS telescope system on Earth, processed to depict mid-infrared as orange and blue, as well as blue in optical light, from one galaxy to another, but this one has a better name. To round out this segment on the shapes of things, we present another Hubble image. Unlike the massive galaxy UGC 10143 in the previous story, this one is about a much closer and smaller system that is anything but a blob. NGC 7184, the Little Sombrero Galaxy, is about the same actual size as its namesake, at 80,000 light-years across. However, the Sombrero Galaxy is twice as close, so it is a bigger angular size in our sky. Both of the Sombrero Galaxies actually resemble the Mexican hat design, at least from our edge-on perspective. And this orientation allows scientists to see the massive clouds of gas and dust above and below the disk of the galaxy, but also hides any spiral structure the systems might have. This image was taken in optical and infrared using the advanced camera for surveys on Hubble to help scientists understand the stars inside the galaxies and learn how they might have evolved. And now, let's get back to our own solar system. Next up, Beth is going to chat with Dani DellaGiustina about the mission extension for Osiris Rex. Stay tuned.
An event I know much of our community is looking forward to is the return of samples from the asteroid Bennu by the Osiris Rex mission. After all, so many of you took the time to map so many rocks. So many rocks. The spacecraft is scheduled to drop that sample off in September of 2023, but what then for the mission? It's not the end. NASA has extended OSIRIS Rex and given it a new name and a new target. Now called OSIRIS-APEX or OSIRIS-Apophis Explorer, the spacecraft is going to swing by and study the infamous asteroid Apophis. The asteroid was discovered in 2004, and calculations performed at the time had it hitting Earth in 2029. However, more recent calculations based on many more observations has saved us from that fate. And now scientists have a chance to get up close and personal with this once deadly asteroid. Leading the team on that mission and joining me today is Dani DellaGiustina from the University of Arizona's Lunar and Planetary Laboratory. Thank you for joining us today, Dani, and welcome.
Yeah, my pleasure.
All right, so how did this mission extension come about? What was the process for getting you to go to Apophis?
Yeah, that is a great question. So the mission concept came about in around the 2019 timeframe, when we knew we had performed really exceptionally on OSIRIS Rex. So our spacecraft had plenty of fuel, and a lot of the limited lifetime items on our spacecraft and our instruments were still in good shape. They still had a lot of life ahead of them. So we started considering what other targets we might be able to send the OSIRIS-REx spacecraft to. And the OSIRIS-REx, both the instruments and the spacecraft were really designed for an asteroid sample return mission, which means getting up close and personal with a small body. And so we examined dozens, really hundreds of objects, asteroids, comets. I think at one point even Venus was in the mix for potential opportunities to send our spacecraft to next. And very few objects had orbits that we could rendezvous with and do an up close and personal survey of when considering all these objects. Fortunately, Apophis was one of the few. And we were all so excited because Apophis, as you mentioned, is a pretty infamous asteroid. A lot of folks in the planetary science community were immediately familiar with it because it has this really close encounter with Earth in the 2029 timeframe. And so we were really excited when we figured out, one, we could do it, and two, the type of science that we could return from sending our spacecraft to an object like Apophis would be really incredible and could answer some pretty important questions. And so we proposed it to NASA in the beginning of this year, and we found out that we got the green light just a couple weeks ago.
So what's the plan for going from dropping off the sample to getting to Apophis?
Well, when we drop off the sample in September of 2023, we need to conduct a divert maneuver immediately afterwards because we don't want the spacecraft to crash into our own planet. And so now, as part of that divert maneuver, we will be putting the spacecraft into a new heliocentric orbit, and it will make several Earth gravity assists in that orbit over about a 5-year period. And that is going to allow us to rendezvous with Apophis in early 2029. Spring of 2029 is when we begin observing it, and summer of 2029 is when we'll actually do the rendezvous.
Wow, so you're saying that you're going to do the close encounter with Apophis about the same time that Apophis is doing the close pass of Earth.
That is correct. So we begin observing Apophis distantly. So Apophis will just look like a point of light about 2 weeks before its close encounter with our planet. And during that time, we'll be able to combine images and get a sense of its rotation rate before the encounter as it is getting tidally torqued. And then post-encounter. So we'll have light curve data during that whole period. And that's really important because we have a lot of indications that Apophis rotation rate will change during the close encounter with our own Earth, that it's going to get torqued, essentially, by the tidal force that's getting exerted across it. And so understanding the rotation rate and how it changes is going to be very important for the OSIRIS-APEX mission.
What kinds of data, other than the torque and changes to its rotation rate, are you hoping to get from the mission?
Oh, there is a lot of data that we are hoping to get from OSIRIS-APEX. So after the close encounter, we'll begin the process of getting inching towards Apophis, so to speak. And while we're doing that, we'll get a sense of what its mass is, and that will inform how we get into orbit around it a little later in the mission. So we want to understand its shape, and we also want to determine what sort of effects the tidal encounter might have had on its surface. So the Apophis encounter with Earth is going to take place at a distance of approximately 1/10 of the lunar distance. And that is really close. That's about, the same distance as geostationary satellites, or excuse me, geosynchronous satellites. And so we know this isn't within what we call the Roche limit, which is the point at which Apophis' self-gravity would be overcome by Earth's gravitational pull on it, and it would begin to disaggregate. But it may be within this sort of ambiguous resurfacing limit that we have some idea about, but we don't have a definitive and clear answer at really how far away from the Earth do you need to be in order for one of these small bodies to get resurfaced. That means, the tidal forces would trigger landslides and might cause some just interesting things to take place, and potentially change its color, reset the effects of space weathering, and so forth. So I'm really personally interested in seeing how exactly the close encounter with Earth is going to affect Apophis' surface. But we'll be doing some additional measurements as the mission progresses to understand its overall composition. And one of the coolest things that we plan to do with OSIRIS-APEX is something called REST, which stands for Regolith Excavation by Spacecraft Thrusters. In this REST event, we're going to get very close to the surface of Apophis with our spacecraft and exert a known force from our spacecraft thrusters in close proximity and see how it displaces any surface material. We witnessed this effect on Bennu during our touch and go, or our tag maneuver, where we collected a sample. We inevitably had to get the spacecraft really close to the surface of Bennu to get that sample. And we noticed we moved material around with the thrusters when we did that. And we've learned a lot from that interaction with this asteroid regolith and the spacecraft thrusters. And so we're hoping we can do this type of experiment at Apophis as well.
One of the things that we've definitely learned about these types of asteroids, particularly with Bennu and Ryugu, is this concept of the rubble pile asteroid, which is sort of electrostatically held together rather than gravitationally compressed. Is Apophis another rubble pile asteroid in that same vein?
All the indications we have to date are that objects that are within the size range of Apophis and Bennu, so Apophis is about 380 meters in its longest dimension. Bennu was a little less than 500 meters in its longest dimension. Objects in the size range we do think are all likely rubble piles. And as they get smaller, maybe at about 100 meters across, we might be transitioning towards monoliths, or just basically one intact rock that is the result of collision, and this is like an impact shard. But we do think Apophis is very likely to be a rubble pile, and one of the big investigations of our APEX mission is to study the structure of Apophis, and so we'll get to test that hypothesis when we get there in 2029.
Are there any plans to map the surface of Apophis similar to how we all did with Bennu?
Yes, absolutely. We will be mapping the surface of Apophis. The end goal for that work is a little different, right? We're not trying to find the best place to gather a sample from and not break our sampling mechanism in the process. But we are really interested in understanding the overall crater retention age, or just how old is the surface of Apophis. And so we'll be counting craters, and the CosmoQuest data that was created from the Bennu images was really instrumental in getting nice crater, crowdsourced crater statistics that we could use to better understand the age of Bennu's surface. We would like to do something really similar at Apophis. And if Apophis is a rubble pile, it will likely have a lot of rocks. And so understanding the size frequency distribution of the boulders on its surface is going to give us a good sense of what sort of processing might have taken place both on Apophis's surface and also what type of processes might have taken place when Apophis was accumulated out of the remnants of its parent body, presumably after a large collision or impact that catastrophically disrupted it.
So we can look forward to counting more rocks. Exciting, exciting news.
Yeah, maybe not quite as many rocks. I think the very few data points we have of other stony asteroids, so Apophis is a stony asteroid, are asteroid Itokawa, which is a similar size to Apophis, and asteroid Eros, which is much larger than Apophis. But on both of those objects, there were areas of relatively smooth, boulder-free regolith. We called them ponds. And so it's likely that Apophis might not be quite as rocky as was the case for Bennu and Ryugu, but we'll find out pretty soon here.
All right. Well, once again, thank you so much for speaking with me today, Dani. I'm sure I speak for everyone when I say we are looking forward to the results of this mission.
Awesome. Thanks, Beth. Thanks so much for your interest in OSIRIS-APEX. And I hope I have the chance to chat with everybody in a couple years when we have rendezvoused with Apophis and are returning some incredible data.
Definitely. Look forward to it. This has been The Daily Space. To all of you watching, this conversation ran longer than we can air here on Now Media. You can catch the interview in its entirety on our website, dailyspace.org.
While you're there, check out our show notes to find more information on all our stories, including images. As always, we're here thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.